Hi everyone. I hope you found this video helpful. If so, I'd really appreciate it if you could subscribe to my channel, like this video, share it with your friends, and leave a positive comment. Your support and encouragement motivate me to create more great videos. In this video, I've covered all the outlines in the syllabus, as shown in the figure.
Linear momentum of the object is defined as the product of its mass and its velocity. So, we get the equation of linear momentum is P equals mv, where m is mass in kilograms, v is velocity in meters per second, p is momentum in kilograms meters per second or Newton second. Momentum is a vector quantity, and its direction is the same as velocity's direction. Newton's laws of motion. Newton's first law state that a body will remain at rest or move with constant velocity unless acted on by a resultant force. So, we can conclude that if no resultant force, so no acceleration, causing the object to be rest or constant velocity. Newton's first law is often called the law of inertia. The inertia of an object is measured by its mass. Mass or inertia is the property of an object that resists change in motion. Newton's third law of motion states that if a body exerts a force on body B, then body B will exert a force on body A of equal magnitude, but in the opposite direction. So, we can conclude that a pair of forces in Newton's third law must be equal in magnitude, opposite in direction, act on different bodies, and same type of forces. Newton's second laws of motion state that a resultant force acting on a body will cause a change in momentum in the direction of the force. So, the resultant force is the rate of change in momentum. So the formula of the resultant force is F equals delta P divided by T, where delta P is change in momentum, which is mv minus mu, and v minus u over T is the acceleration, a. So, the resultant force can be written as F equals ma. From this equation, we moves T to multiply with F, like this. The product of F and T is defined as the impulse, I. So, the impulse is the change in momentum or the product of resultant force and time. The impulse is a vector quantity, and its unit is the same as momentum's unit. We can conclude the Newton's second law of motion that if the resultant force is not zero, causing the velocity to change and the object will be accelerated or decelerated. If a ball of mass, m, kilograms is hit a wall at a speed, u, it bounces back with a speed, v. The collision time, t, as shown. We use a negative sign to represent the left direction. The change in momentum is mov minus mu, substituting the negative v to indicate the left direction, like this. So, the change in momentum is negative mv plus mu. The negative sign indicates that the change in momentum of the mass to the left direction. During the hitting the mass, m exerts a force on the wall with equal in size and opposite in direction as the wall exerts a force on the mass m. This is because Newton's third law of motion about action and reaction. The forces act on the mass and the wall for the same amount of during time, t. The graph of the average force F against the collision time, t of the collision between the mass, m, and wall is shown. So, the area under graph is the change in momentum or impulse. The graph of momentum, p, of the mass, m, against during time, t, is shown. The gradient of the graph is change in momentum over change in time, which is the resultant force. So the magnitude of the resultant force is negative mv plus mu over t. This is the magnitude of resultant force. The negative sign indicates the left direction. Therefore, the gradient of the graph is the force of the mass to act on the wall, or the force of the wall acting on the mass. Work example 1. A small pebble of mass 500 grams is attached to the lower end of a light string. A. Find the tension in the string when the pebble is moving upwards with an acceleration of 2 meters per second squared. We convert the mass in grams into kilograms. By dividing 500 with 1000, we get mass equals 0.5 kilograms. The free body diagram of the pebble, there are weight to act down and the tension acting upward. From the equation, F equals ma. F is the resultant force to act on the pebble upward due to it moves upward. So, F equals T minus W equals ma. Substituting W equals 0.5 times 9.81, m equals 0.5 and A equals 2. We solve the tension T to get T equals 5.9 newtons for two significant figures. B. Find the tension in the string when the pebble is moving downwards with an acceleration of 3 meters per second squared. From the equation, F equals ma. F is the resultant force to act on the pebble downward due to it moves downward. So, F equals W minus T equals ma. Substituting W equals 0.5 times 9.81, m equals 0.5 and A equals 3. We solve the tension T to get T equals 3.4 newtons for two significant figures. C. Find the tension in the string when the pebble is moving downwards at a constant speed of 5 meters per second. From the equation, F equals ma. F is the resultant force to act on the pebble. It is 0 due to constant speed and its acceleration is 0. So, W minus T equals 0. And then W equals T equals 0.5 times 9.81. We get the tension T equals 4.9 newtons for two significant figures. D. Find the tension in the string when the pebble is moving downward with a deceleration of 4 meters per second squared. From the equation, F equals ma. F is the resultant force to act on the pebble downward due to it moves downward. So, F equals W minus T equals ma. Substituting W equals 0.5 times 9.81, m equals 0.5 and A equals -4 due to deceleration. We solve the tension T to get T equals 6.9 newtons for two significant figures. Work example 2. P and Q of masses 2 kg and 3 kg are attached to the ends of a light inextensible string that passes over a smooth pulley. The system is released from rest. A. Find the acceleration of each mass. The free body diagram of P, there are weight 2, g, to act down and the tension T acting upward. G is the acceleration of free fall, which is 9.81 meters per second squared. The free body diagram of Q, there are weight 3, g, to act down and the tension T acting upward. The tensions T act on P and Q are the same due to same tension in same string. The mass Q moves downward and mass P moves upward with same acceleration, A, because mass of Q is more than mass of P. This causes the acceleration of Q downward and the acceleration of P upward. We write the equation of motion for P and Q from the equation F equals ma. The resultant force F on P is upward due to its acceleration upward. The equation of motion of P is T minus 2g equals 2a. The resultant force F on Q is downward due to its acceleration downward. The equation of motion of Q is 3g minus T equals 3a. We add two equations together, so we get g equals 5a. We solve the acceleration, a, by subtracting g equals 9.81. We get the acceleration, a, equals 2.0 meters per second squared for two significant figures. B. Find the tension in the string. We substitute the acceleration, a, into the equation of motion of P or Q. So, I use the equation of motion of P. Substituting a equals 1.962 and g equals 9.81. We get the tension T equals 24 newtons for two significant figures. C. Find the force exerted on the pulley. Two tension T act on the pulley downward, like this. So, the resultant force exerts on the pulley downward with magnitude 2, T. Substituting T equals 23.5 for 4 newtons. We get the resultant force, F, equals 47 newtons for two significant figures. D. Find the distance moved by Q in the first 4 seconds. We calculate the distance using the kinematic equations due to constant acceleration. We use the positive sign to indicate downward direction. When Q moves downward, the displacement, S, need to be found, the initial velocity, U, equals 0, the final velocity, V, is unknown, the acceleration, A, equals 1.962 and time, T, equals 4. We use the equation S equals U, T, plus half of A, T squared. Substituting U equals 0, T equals 4, A, equals 1.962. We get the distance equals 16 meters for two significant figures. Exam style question 1. A box of mass 8 kilograms rests on a horizontal rough surface. A string attached to box passes over a smooth pulley and supports a 2 kilograms mass at other end. When the box is released, a frictional force of 6 newtons acts on it. What is the acceleration of the box? The mass 2 kilograms moves downward to pull the box 8 kilograms to the right with same acceleration. This causes the acceleration of mass 2 kilograms downward and the acceleration of box 8 kilograms to the right. The free body diagram of the box 8 kilograms, there are the tension T to act rightward, and the frictional force acts to the left, like this. The free body diagram of the mass 2 kilograms, there are the tension T to act upward, and the weight 2g acts downward, like this. G is the acceleration of free fall, which is 9.81 meters per second squared. We write the equation of motion for P and Q from the equation F equals ma. The resultant force F on box is point leftward due to its acceleration leftward. The equation of motion of box 8 kilograms is T minus 6 equals 8a. The resultant force F on mass 2 kilograms is downward due to its acceleration downward. The equation of motion of mass 2 kilograms is 2g minus T equals 2a. We add two equations together, so we get 2g minus 6 equals 10a. Substituting g equals 9.81. We get the acceleration, a, equals 1.4 meters per second squared for two significant figures. Exam style question 2. A golf ball of mass m is dropped onto a hard surface from a height h1 and rebounds to a height h2. The momentum of the ball just as it reaches the surface is different from its momentum just as it leaves the surface. What is the total change in the momentum of the golf ball between these two instants? Ignore air resistance. We calculate the velocity of mass m that hits the surface using the kinematic equations due to constant acceleration as gravity g. We use the negative sign to indicate the downward direction. When the mass m drops from rest to the hard surface, the displacement, s, equals negative h1, the initial velocity, u, equals 0, the final velocity, v, equals v1, the acceleration equals negative g, and time t is unknown. We use the equation v squared equals u squared plus 2as. Substituting v equals v1, u equals 0, a equals negative g, and s equals negative h1. We get the velocity v1 equals negative square root of 2, g, h1. The negative sign indicates downward. When the mass m moves upward, the displacement, s, equals h2, the initial velocity, u, equals v2, the final velocity, v, equals 0, the acceleration, a, equals negative g, and time t is unknown. We use the equation v squared equals u squared plus 2as. Substituting v equals 0, u equals v2, a equals negative g, and s equals negative h2. We get the velocity v2 equals square root of 2, g, h2. The change in momentum is mv minus mu. Substituting v2 and v1 like this. We get the change in momentum like this. Exam style question 3. Water is pumped through a hosepipe at a rate of 90 kilograms per minute. It emerges from the hosepipe horizontally with a speed of 20 meters per second. What force is required from a person holding the hosepipe to prevent it moving backwards? When the water moves from the hosepipe, there is force to push the water out. This causes the force to act the hand backward in equal size due to Newton's third law. this force is equal to the force required to hold the hosepipe. We calculate this force by the equation F equals m/v minus mu over T. The mass per second is 90 divided by 60, it is 1.5 kilograms per second. Substituting m per t equals 1.5, final velocity v equals 20, and initial velocity u equals 0. We get the force equals 30 newtons. Exam style question 4. Two blocks x and y of masses m and 3m respectively are accelerated along a smooth horizontal surface by a force F applied to block x as shown. What is the magnitude of force exerted by block x on block y during this acceleration? We calculate the acceleration of two blocks from the equation F equals ma. F is the resultant force and m is the combined mass of x and y. We get the acceleration a equals F over 4m. The free body diagram of block x, there are the force F and the force exerted by y. The free body diagram of block y, there is force exerted by x. The force exerted by y on x equals the force exerted by x on y due to Newton's third law. Two blocks move with same acceleration, like this. We calculate the magnitude of force exerted by block x on block y by the equation F equals ma. Substituting F equals force on y, m equals 3m and a equals F over 4m. We get the force on y equals 3F over 4. Exam style question 5. A 1.2 kilograms mass is supported by a person's hand and 2 Newton meters as shown. When a person's hand is removed, what is the vertical acceleration of the mass? We break the force for newtons into vertical component as 4 cos 37 degrees, upward. The force 3 newtons break into vertical component as 3 cos 53 degrees, upward. We calculate the acceleration by the equation F equals ma. The resultant force F equals 12 minus 3 cos 53 degrees, minus 4 cos 37 degrees. Substituting m equals 1.2. We get the acceleration a equals 6.0 meters per second squared. Exam style question 6. The graph shows the variation with time of the momentum of a ball as it is kicked in a straight line. Initially, the momentum is p1 at the time t1. At the time t2 the momentum is p2. What is the magnitude of average resultant force acting on the ball between t1 and t2? We calculate the resultant force by the equation F equals change in momentum, delta p, over time t. The change in momentum, delta p, equals negative p2 minus p1. We get the resultant force F equals negative p2 plus p1 over t. The negative sign indicates the direction. The magnitude of the resultant force is this. Mass and weight. Mass is a measure of the amount of matter in an object at rest that resisting its movement. Mass is a scalar quantity and its unit is kilograms. Mass is constant anywhere in the universe. Weight is a gravitational force on an object that has mass. Weight is a vector quantity and its unit is newtons. Weight varies anywhere in the universe due to the gravitational field strength. We calculate the weight of the mass by this equation. Exam style question 7. A man weighs 240 newtons Mars where the acceleration of free fall g is 4 meters per second squared. On the moon, g is 2 meters per second squared. Which statement is correct? The mass of the man remains the same at any position in the universe. We calculate the mass of the man by the equation m equals w over g. Substituting w equals 240 newtons on Mars and g of Mars equals 4. We get the mass of the man equals 60 kilograms. The weight of the man depends on the acceleration of free fall g. So, the weight of the man on the moon calculate by the equation w equals mg. Substituting m equals 60 and g equals 2. We get the weight of the man on the moon equals 120 newtons. The man has a mass on Mars of 60 newtons, this is incorrect. B. The man has a mass on the moon of 120 kilograms. This is incorrect. C. The man weighs 120 newtons on the moon. This is correct. D. The man weighs 240 newtons on the moon. This is incorrect.
Hi everyone. I hope you found this video helpful. If so, I'd really appreciate it if you could subscribe to my channel, like this video, share it with your friends, and leave a positive comment. Your support and encouragement motivate me to create more great videos. In this video, I've covered all the outlines in the syllabus, as shown in the figure.
Frictional forces. Friction is a force that opposes the movement of an object. It acts in the direction opposite to the motion. Friction is present almost everywhere, and it can slow down or even stop moving objects. This happens because friction converts kinetic energy into thermal energy. Viscous or drag forces. Viscous or drag forces are the frictional force in a fluid. This is the resistance an object experiences when moving through a fluid. Two main factors affecting fluid friction. The surface area of the object in contact with the fluid increases, drag also increases. The object's speed increases, drag also increases. Terminal velocity in air. A badminton shuttlecock, dropped from rest, will reach terminal velocity as it falls through the air. At the start, the initial velocity is 0, and initial drag forces is also 0. This causes the resultant force equal weight acting downward, causing the initial acceleration is equal to the acceleration of free fall. When the badminton shuttlecock moves downward, its speed increases from 0, causing the drag force to increase from 0. This causes the resultant force decreases to act downward, and it is equal to weight minus drag force, so the acceleration is also decreased. When the badminton shuttlecock moves downward, its speed increases to maximum, which is called terminal velocity, causing the drag force to increase to equal weight. The resultant force is 0 because weight equals drag force, so the acceleration is also 0 and speed remains constant. The graph of displacement varies with time t of this motion is shown, like this. Recall that the gradient of displacement time graph is velocity. This section shows that the velocity increases from 0 to a maximum as its gradient increases to a maximum. This section shows that maximum constant velocity occurs due to the maximum constant gradient. The graph of velocity varies with time t of this motion is shown, like this. Recall that the gradient of velocity time graph is the acceleration. As the velocity increases but the acceleration decreases due to the gradient decreases until the velocity is constant and the acceleration is 0. This constant velocity is terminal velocity. The graph of acceleration varies with time t of this motion is shown, like this. The initial acceleration is equal the acceleration of free fall and then it decreases until 0 when reached terminal velocity. Assuming the blue ball has a larger mass than the green ball but same size, both dropped from the same height at the same time, the blue ball will likely reach the ground first and with a higher terminal velocity. This is because the blue ball has bigger mass, so bigger weight too, causing it accelerate for a longer time before drag force to equal weight, leading it reaches higher terminal velocity and reaching the floor faster. The green ball has smaller mass, so smaller weight too, causing it accelerate for a shorter time before drag force to equal weight, leading it reaches lower terminal velocity and reaching the floor slower. The graph of velocity varies with time t for both balls is shown, like this. The blue ball reaches the floor first with higher terminal velocity, like this. The green ball reaches the floor later with lower terminal velocity, like this. Viscous or drag force of liquid is the resistance force when an object travels through a liquid. It depends on the shape, speed, and temperature of liquid. A metal sphere, dropped from rest, will reach terminal velocity as it falls through the liquid like as shown. At the start, the resultant force acts on the metal is weight minus upthrust, causing it accelerate downward and its velocity increases. the drag force increases upward as velocity increases, so the resultant force is weight minus upthrust minus drag force, causing the resultant force to decrease and acting downward, leading to the acceleration also decreases and the velocity increases at slower rate. The drag force increases until the resultant force is zero, meaning that weight is equal to upthrust plus drag force, causing the acceleration is also zero and the velocity remains constant. This is called terminal velocity. Recall that the upthrust and weight are always constant, while drag force increases from zero to maximum when a ball reaches terminal velocity. Exam style question 1. A sphere of radius r is moving through a fluid with constant speed v. There is a frictional force F acting on the sphere, which is given by the expression F equals 6 pi dr v, where d depends on the fluid. 1. Show that the SI base units of the quantity d are kilograms per meter per second. The derived unit of force F is kilograms meters per second squared. The SI base unit of radius r is meter. The derived unit of speed v is meters per second. We rearrange the equation and making d is the subject, like this. We find the derived unit of d by substituting the derived units of f, r, and v, like this. We simplify the derived unit of d, like this. We get the derived of d is kilograms per meter per second. 2. A raindrop of radius 1.5 mm falls vertically in air at a velocity of 3.7 meters per second. The value of d for air is 6.6 times 10 power negative for kilograms per meters per second. The density of water is 1000 kilograms per cubic meter. 1. Calculate the magnitude of the frictional force F. We substitute d equals 6.6 times 10 power negative 4, r equals 1.5 times 10 power negative 3 meters, and v equals 3.7 meters per second. We get the force F equals 6.9 times 10 power negative 5 newtons for two significant figures. 2. Calculate the acceleration of the raindrops. When the raindrops moves downward, like this, there are the weight acting downward and the frictional force acting upward, causing the raindrop to accelerate downward. We calculate the acceleration from the equation F equals ma. F is the resultant force, which is mg minus F equals ma. We rearrange the equation to isolate the acceleration, like this. Where m is mass, it calculates by multiplying density ρ times volume v. The raindrop is sphere, so the volume v is for over 3 pi r cubed. Substituting g equals 9.81, F equals 6.9 times 10 power negative 5, ρ equals 1000, r equals 1.5 times 10 power 3. We get the acceleration equals 4.9 meters per second squared for two significant figures. B. The variation with time t of the speed v of the raindrops in A is shown in the graph below. 1. State the variation with time of the acceleration of the raindrop. The gradient of velocity time graph is the acceleration. At t equals 0 second, the initial acceleration equals g. And then the acceleration decreases as time increases due to the gradient decreases. Until the acceleration is 0 when the gradient of graph is 0. 2. A second raindrop has a radius that is smaller than that given in A. On the graph, sketch the variation of speed with time for a second raindrop. Smaller radius causes the weight and the frictional force decreases, but weight decrease greater that frictional force, so the raindrop will be reach the terminal velocity faster and lower. We draw the graph like this. Exam style question 2. A skydiver jumps from a high-altitude balloon. A. 1. Explain briefly why the acceleration of the skydiver decreases with time. Drag force increases as speed increases, causing the resultant force decreases. 2. Explain briefly why the acceleration of the skydiver is 9.8 meters per second squared at the start of the jump. The resultant force is weight acting downward, and no drag force. B. The variation with time t of the vertical speed v of the skydiver is shown in the graph below. Use the graph to determine the magnitude of the acceleration of the skydiver at time t equals 6 seconds. We calculate the acceleration by the gradient of velocity time graph. We draw the tangent at t equals 6 seconds, like this. We draw the large triangle, like this. Delta y equals 30 minus 12 is equal to 18, like this. Delta x equals 11.2 minus 1.6 is equal to 9.6, like this. We calculate the gradient equals 18 over 9.6. We get the acceleration equals 1.9 meters per second squared for two significant figures. You got marks if the acceleration is in range 1.7 to 2.1 meters per second squared. C. The skydiver and his equipment have total mass 90 kilograms. 1. Calculate for the skydiver and his equipment the total weight. We calculate the weight by the equation W equals mg. Substituting m equals 90 kilograms and g equals 9.81 meters per second squared. We get the weight equals 880 newtons for two significant figures. 2. Calculate for the skydiver and his equipment the acceleration force at time t equals 6 seconds. We calculate the resultant force by the equation F equals ma. Substituting m equals 90 kilograms and a equals 1.875 meters per second squared. We get the weight equals 170 newtons for two significant figures. 3. Use your answer in 1 and 2 to determine the total resistance force acting on the skydiver at time t equals 6 seconds. We calculate the resistance force by the equation F equals ma. F is the resultant force, which is W minus resistance force equals ma. So, resistance force equals W minus ma. Substituting W equals 882.9 newtons and ma equals 168.75 newtons. We get the resistance force equals 710 newtons for two significant figures.
Hi everyone. I hope you found this video helpful. If so, I'd really appreciate it if you could subscribe to my channel, like this video, share it with your friends, and leave a positive comment. Your support and encouragement motivate me to create more great videos. In this video, I've covered all the outlines in the syllabus, as shown in the figure.
Principle of conservation of momentum states that the total momentum of a closed system before an interaction is equal to the total momentum of that system after the interaction. A closed system, that is, a system on which no external forces act. Momentum in collisions. The total momentum of objects that collide remains the same. This is called conservation of momentum. This means that the total momentum before collision to equal the total momentum after collision. When a ball A with mass, ma, collides to a ball B with mass m, b, like this. During the impact each ball exerts a force on the other with equal in size and opposite in direction. This is because Newton's 3 law about action and reaction, so negative Fa equals Fb. These forces act each ball for the same amount of during time t. This means that F times t being equal in magnitude but opposite in direction for each ball, like this. Fa times t is the change in momentum of ball A. Fb times t is the change in momentum of ball B. The negative shows that both change in momentum are in opposite direction. Before the collision, the initial velocity of the ball A is u, a, and the initial velocity of the ball B is u, b. After the collision, the final velocity of the ball A is v, a, and the final velocity of the ball B is v, b. So, the change in momentum of ball A is equal in magnitude but opposite in direction to the change in momentum of ball B. We rearrange the equation like this. This ensures that the total momentum before the collision remains equal to the total momentum after the collision. Exam style question 1. A wooden block is freely supported on brackets at a height of 4 meters above the ground, as shown. A bullet of mass 5 grams is shot vertically upwards into the wooden block of mass 95 grams. It embeds itself in the block. The impact causes the block to rise above its supporting brackets. The bullet hits the block with a velocity of 200 meters per second. How far above the ground will the block be at the maximum height of its path? When the bullet hits the block with a velocity of 200 meters per second, they stick together with a speed v, as shown. We calculate the speed v of the bullet and the block by the total momentum before collision equals total momentum after collision. First, we convert the masses to kilograms. Bullet mass, 5 grams equals 0.005 kilograms. Block mass, 95 grams equals 0.095 kilograms. So, the total mass of the bullet and wooden block is 0.1 kilograms. The momentum of the bullet before the collision equals 0.005 times 200. The momentum of the block after the collision equals 0.095 times 0, due to the block rest. The momentum of the bullet and block after the collision equals 0.1 times v, due to they stick together. We get the speed v equals 10 meters per second. When both bullet and block rise above its supporting bracket to reach the maximum height at their speed is 0, as shown. During this moment, the displacement s need to find, the initial velocity u equals 10, the final velocity v equals 0, the acceleration equals negative 9.81 due to downward direction, and time t is unknown. We calculate the displacement s by iv squared equals u squared plus 2 a s. Substituting v equals 0, u equals 10, a equals negative 9.81. We get the displacement s equals 5.0968 meters. So, the total distance from the ground equals 9.1 meters for two significant figures. Collision in 2 dimensions. A ball A of mass, ma, with a velocity u, moving towards a stationary ball B of mass, mb. The balls collide. After the collision, ball A moves off with velocity va, at an angle theta to its original velocity, and ball B moves with a velocity vb, at an angle of beta to the original velocity of A. We break va into horizontal component as va cos theta and vertical component as va sin theta, like this. We break vb into horizontal component as vb cos beta and vertical component as vb sin beta, like this. Horizontally, total momentum before collision equals ma u. This is because momentum of ball B is 0. Horizontally, total momentum after collision equals ma va cos theta plus mb vb cos beta. Vertically, total momentum before collision equals 0. This is because vertical momentum of both balls is 0, as both balls move in horizontally along x-axis. Vertically, total momentum after collision equals ma va sin theta plus negative mb vb sin beta. The negative sign indicates downward direction. The momentum must be conserved during the collision. The total momentum before collision is shown by the momentum vector of ma u, like this. The total momentum after collision is shown by the sum of the momentum vector of ma va and mb vb, like this. This shows that ma u equals ma va plus mb vb. We can resolve the momentum as follows. Horizontally, the total momentum is conserved. So, ma u equals ma va cos theta plus mb vb cos beta. Vertically, the total momentum is conserved. So, 0 equals ma va sin theta negative mb vb sin beta. Exam style question 2. A ball X moves along a horizontal frictionless surface and collides with another ball Y, as illustrated in figure. The balls stick together during the collision and then travel along line AB, as illustrated in figure A1. Calculate, to 3 significant figures, the component of the initial momentum of ball Y that is perpendicular to line AB. We break a velocity of ball y into horizontal and vertical components as follows: 6 cos 60 degrees and 6 sin 60 degrees. We calculate the momentum by P equals mv. So, the component of the initial momentum of ball y that is perpendicular to line AB equals 0.200 times 6.00 sin 60 degrees. We get the answer is 1.04 kilograms meters per second for 3 significant figures. 2. By considering the component of the initial momentum of each ball perpendicular to line AB, calculate, to 3 significant figures, Vx. We break a velocity of ball x into horizontal and vertical components as follows: Vx, cos 60 degrees and Vx, sin 60 degrees, downward. Vertically, the total momentum is conserved. Vertical momentum of ball x before the collision equals negative 0.300 times Vx, sin 60 degrees. The negative sign indicates the downward direction. Vertical momentum of ball y before the collision equals 0.200 times 6.00 sin 60 degrees. Vertical momentum of both balls after the collision equals 0, because they don't move in vertical. We get the speed Vx equals 4.00 meters per second for 3 significant figures. 3. Show that the speed of the 2 balls after the collision is 2.4 meters per second. We give the speed of 2 balls after the collision equals v. Horizontally, the total momentum is conserved. Horizontal momentum of ball x before the collision equals 0.300 times Vx, cos 60 degrees. Horizontal momentum of ball y before the collision equals 0.200 times 6.00 cos 60 degrees. Horizontal momentum of 2 balls after the collision equals 0.500 times v. We get the speed v equals 2.4 meters per second. This is shown. Exam style question 3. 2 balls, x and y, move along a horizontal frictionless surface, as illustrated in figure below. The 2 balls collide at point B. The balls stick together and then travel along the horizontal surface in a direction at right angles to line AB, as shown in figure above. A. By considering the components of momentum in the direction from A to B, show that the ball X has a mass of 4 kilograms. We break the velocity 9.6 meters per second into vertical and horizontal components as follows: 9.6 sin 60 degrees and 9.6 cos 60 degrees, as shown. Horizontally, the total momentum is conserved. Horizontal momentum of the ball x before the collision equals mx times 3.0. Horizontal momentum of the ball y before the collision equals negative 2.5 times 9.6 cos 60 degrees, the negative sign indicates the left direction. Horizontal momentum of 2 balls after the collision equals 0, because they move only in the vertical. We get the mass mx equals 4.0 kilograms. This is shown. B. Calculate the common speed v of the 2 balls after the collision. Vertically, the total momentum is conserved. Vertical momentum of the ball x before the collision equals 0, because it moves in only horizontal. Vertical momentum of the ball y before the collision equals 2.5 times 9.6 in 60 degrees. Vertical momentum of 2 balls after the collision equals 6.5 times v. We get the speed v equals 3.2 meters per second for 2 significant figures. C. Determine the difference between the initial kinetic energy of ball x and the initial kinetic energy of ball y. Kinetic energy of ball x before the collision equals half of 4 times 3 squared, resulting in 18 joule. Kinetic energy of ball y before the collision equals half of 2.5 times 9.6 squared, resulting in 115.2 joule. So, the difference in kinetic energy equals 97 joule for 2 significant figures. Types of collisions. When the ball mass m, a, with the speed u, a, collides with the ball mass m, b, with the speed u, b, after the collision the ball mass m, a, moves with the speed v, a, and the ball mass m, b, moves with the speed v, b. Total momentum before the collision like this. Total momentum after the collision like this. Total kinetic energy before the collision like this. Total kinetic energy after the collision like this. There are two types of the collision as elastic collisions and inelastic collisions. Elastic collisions. The momentum is conserved during elastic collisions, so total momentum before the collision equals total momentum after the collision. The kinetic energy is conserved during elastic collisions, so total kinetic energy before the collision equals total kinetic energy after the collision. The relative speed of approach is equal to the relative speed of separation during the elastic collisions. Inelastic collisions. The momentum is conserved during inelastic collisions, so total momentum before the collision equals total momentum after the collision. The kinetic energy is not conserved during inelastic collisions, so total kinetic energy before the collision is more than total kinetic energy after the collision. The relative speed of approach is not equal to the relative speed of separation during the inelastic collisions. When the ball A with a speed 5 meters per second to the right and the ball B with a speed 8 meters per second to the right. So, the relative speed equals 8 minus 5 is equal to 3 meters per second. When the ball A with a speed 4 meters per second to the left and the ball B with a speed 6 meters per second to the left. So, the relative speed equals 6 minus 4 is equal to 2 meters per second. When the ball A with a speed 4 meters per second to the right and the ball B with a speed 5 meters per second to the left. So, the relative speed equals 4 plus 5 is equal to 9 meters per second. When the ball A with a speed 2 meters per second to the left and the ball B with a speed 3 meters per second to the right. So, the relative speed equals 2 plus 3 is equal to 5 meters per second. Therefore, the relative speed between two objects is calculated as follows. Subtracting their speeds when they move in same directions. Adding their speeds when they move in opposite directions. Exam style question 4. Two spheres approach each other along the same straight line. Their speeds are u1 and u2 before collision, and v1 and v2 after collision, in the direction shown below. Which equation is correct if the collision is perfect elastic? The relative speed of approach is equal to the relative speed of separation during elastic collision. The relative speed of approach is u1 plus u2. The relative speed of separation is v1 minus v2. So, D is correct. Exam style question 5. The diagram shows two spherical masses approaching each other head-on at an equal speed u. One has mass 2m and the other has mass m. Which diagram showing the situation after the collision shows the result of an elastic collision? The relative speed of approach is equal to the relative speed of separation during elastic collision. The relative speed of approach is u plus u equals 2u. A. The relative speed of separation is 2u, this is correct. B. The relative speed of separation is 5u over 6, this is incorrect. C. The relative speed of separation is u over 2, this is incorrect. D. The relative speed of separation is 0, this is incorrect. Exam style question 6. A. State Newton's third law of motion. If body A exerts a force on body B, then body B will exert a force on body A of equal magnitude but in the opposite direction. B. A block X of mass, mx, slides in a straight line along a horizontal frictionless surface, as shown in figure below. The block X, moving with speed 5v, collides head-on with a stationary block Y of mass, my. The two blocks stick together and then move with common speed v, as shown. 1. Use conservation of momentum to show that the ratio my to mx is equal to 4.0. The momentum of block X before the collision equals mx times 5v. The momentum of block Y before the collision equals 0, because it is stationary. The momentum of two blocks after the collision equals mx plus my times v. We simplify and rearrange the equation like this. We get the ratio equals 4.0. 2. Calculate the ratio total kinetic energy of X and Y after collision to total kinetic energy of X and Y before collision. Total kinetic energy of X and Y before the collision is half of the sum mx and my times v squared. Total kinetic energy of x and y after the collision is half of mx times 5v squared. We simplify the equation like this. Substituting the ratio of my to mx is 4. We get the ratio of kinetic energy is 0.20. 3. State the value of the ratio in 2 for a perfect elastic collision. The ratio is 1. This is because the kinetic energy is conserved for a perfect elastic collision, meaning that total kinetic energy before the collision equals total kinetic energy after the collision. C. The variation with time t of the momentum of block x in B is shown in figure below. Block x makes contact with block y at time t equals 20 milliseconds. 1. Describe, qualitatively, the magnitude and direction of the resultant force, if any, acting on block x in the time interval. T equals 0 to 20 milliseconds. The resultant force equals 0. This is because the speed and momentum is constant. T equals 20 milliseconds to t equals 40 milliseconds. The resultant force is constant and opposite direction to the movement, or momentum. This is because the gradient of the graph is the resultant force, and its gradient is constant and negative. 2. On figure above, sketch the variation of the momentum of block y with time t from t equals 0 to t equals 60 milliseconds. The momentum of block y is 0 between t equals 0 to 20 milliseconds, because it is stationary. So, we draw the graph like this. The momentum of block y increases from 0 between t equals 20 to 40 milliseconds to this. This is because total momentum before the collision is equal to total momentum after collision. Total momentum before the collision equals 5. Total momentum after the collision must be 5. Momentum in explosion. The conservation of momentum principle can be applied to explosions. The total momentum of the system before the explosion is equal to the total momentum of the system after the explosion, although there will be a significant increase in the total kinetic energy of the fragments. An explosion involves a rapid release of energy, causing an object to break apart into pieces that fly in different directions. Let's consider an object with mass m that is stationary before the explosion, so its momentum is 0. The object explodes into two fragments with masses m1 and m2, which move apart at velocities v1 and v2, respectively. The total momentum after the explosion is the sum of the momenta of the two fragments m1, v1, plus m2, v2. Momentum is conserved when during explosion. So, total momentum before explosion equals total momentum after explosion. Then, 0 equals m1, v1, plus m2, v2. And m1, v1 equals minus m2, v2. This equation tells us that the momentum of fragment m1 is equal in magnitude but opposite in direction to the momentum of fragment m2. As the rocket burns the fuel, generating hot gases that are ejected at high speeds from the rocket. This produces the momentum large amount of fast-moving gases out of the back of the rocket. So, the rocket gains an equal amount of momentum in the opposite direction to that of the moving exhaust gases. Exam style question 7. A stationary explodes into two components of mass m and 2m. The compellentors gain kinetic energies x and y respectively. What is the value of the ratio x to y? We give a velocity of mass m is v, x, and velocity of mass 2m is v, y. We find the velocity v, x, first using the principle of conservation of momentum. Total momentum before the explosion equals 0, due to it is stationary. The momentum of mass m after the explosion equals negative m times v, x, the negative sign indicates the left direction. The momentum of mass 2m after the explosion equals 2m times v, y. We rearrange and simplify the equation, like this. We get the velocity v, x, equals 2v, y. The kinetic energy x equals half of m, v, x, a squared. The kinetic energy y equals half of 2m, v, y, r squared. We simplify the equation, like this. Substituting v, x, equals 2v, y, like this. We simplify the equation, like this. We get the ratio of x to y equals 2. Exam style question 8. A stationary nucleus has nucleon number k. The nucleus decays by emitting a proton with speed v to form a new nucleus speed u. The new nucleus and the proton move away from one another in opposite directions. What is the speed v in term of a and u? The nucleon number is mass number, and it can be represented mass. So, mass of a proton equals 1 and mass of a new nucleus equals a-1. We find the velocity v of a proton using the principle of conservation of momentum. Total momentum before decay equals 0, due to a nucleus is stationary. The momentum of a proton after decay equals -1 times v, the negative sign indicates the left direction. The momentum of a new nucleus after decay equals a-1 times u. We get the velocity v equals a-1 times u.
I hope you found this video helpful. If you did, I would be grateful if you would subscribe, share, like and leave a positive comment. Your support will encourage me to create more content. Thank you.